Hey guys, Mr. Backerberg here. In this video, we're going to look at optimization examples from business.
So to optimize something means that we're trying to maximize or minimize some aspect of it. So for example, what is the size of the most profitable production run of whatever product it is that we're making? Or what is the least expensive shape for an oil can? Or what's the stiffest rectangular beam that we can cut from a 12-inch log? So always trying to maximize or minimize some specific aspect of whatever it is that we are optimizing. So in this example, we're going to be making an open style box, and what we're going to do is cut out congruent squares of side length X from the corners of a 20 by 25 inch sheet of tin, and then we're going to bend up the remaining sides to make the box. We want to figure out how large those squares should be in order to make a box that holds as much as possible, and then we also want to figure out what the resulting volume would be. So I'm going to sketch out a picture of what's happening here. We are starting with a rectangular sheet of tin that is 20 by 25 inches, and what we're going to be doing is cutting squares out of the corners to then create these flaps that we're going to then fold up to become the sides of our box. And the side length of these squares, that length is going to be some X value. Now we're really trying to maximize the volume of this box. So if we think about the volume of a box or a rectangular prism, that volume formula is the length times the width times the height. Well, let's look at this side that's 20 inches long first. It started out as 20 inches long, but what's going to happen is we're going to cut this X chunk off of each side. So this piece is X and this piece is X. So then the length here would be 20 minus 2 of those X values, since we're cutting X off of each side. Now if we look at how wide this box is, our rectangle started at 25 inches wide, but again, we're cutting this X chunk off of each side. So this is going to be 25 inches minus 2 of those X's, again, because we're cutting that off of each side. Now, as we take these flaps and fold them up, whatever this X value is going to end up being the height of our box. So this multiplication in here is going to lead us to the volume of our box. Now, if we think about an implied domain for our function, I want to focus on this shortest side that started at 20 inches long. These X values really represent chunks that we're cutting off of each side. So as far as the smallest possible amount that we'd be able to cut off of each side, that's 0. But if we don't cut anything off of each side, then we're not really creating a box. Because the shortest side is 20, then the amount that we can cut off of each side as far as a maximum goes would be 10 inches. Because if you cut 10 inches off of one side and 10 inches off of the other side, that's 20 inches. And again, that doesn't really create a box, but that'll lead us into our domain here. Now, if we were to go through and actually multiply everything out in here to turn these different factors into just one polynomial function, that would end up being 4x cubed minus 90x squared plus 500x. So this function, again, represents our volume. But when we're optimizing things, we want to take a look at the derivative of this volume function. So v prime is going to be 12x squared, using the power rule, minus 180x plus 500. Now, to find our critical numbers, we want to take this and set it equal to 0. But as I'm looking at it, it doesn't really look like it's going to factor out nicely. So I'm thinking that we're probably going to have to do the quadratic formula with this. So that's going to be the opposite of our b value plus or minus the square root of that b value squared minus 4 times the a value times the c value all over 2 times the a value. Now, as we're working on simplifying things down, underneath that radical, we should end up with the square root of 8,400. So we get 180 plus or minus the square root of 8,400, all divided by 24. Now that 8,400 doesn't square root nicely, so we are going to end up with some decimals in here. So if we split this up and do the 180 plus the square root of that 8,400, all divided by 24, that's going to give us about 11.32 if we were to type that into our calculator. And then if we did the 180 minus the square root of 8,400, all divided by 24, that's going to give us about 3.68. Now, as we're looking at these potential x values, we want to keep in mind that domain that we talked about earlier. We said that our domain was going to run from 0 to 10. So getting this x value of 11.32 would mean that we're trying to cut 11 inches off of each side. But since one of the sides is only 20 inches long, you can't cut 11 inches off of one side and 11 inches off of the other side. You'll run out of material. So this 11.32 doesn't work as far as the context of this problem. So we're really focusing on the 3.68. Now, along with this critical number that we just came up with, we also want to test out our endpoints of our domain. So we're going to test out this x value of 3.68, but we're also going to test out the x value of 0 and the x value of 10. Now, as far as doing the volume, here's our volume formula right here. Let's start with the 0 and talk about why this one doesn't really make sense. If we were to plug in 0 for all of those x's, well, this front term would turn into 0, this middle term would turn into 0, and this last term would turn into 0. So if you don't cut anything off of the sides, you get a volume of 0 because you can't really build the box. So for the x value of 0, we get a volume of 0. That doesn't really make sense in the context of our problem because we want a box that has more than a 0 volume. Now, something similar is going to happen if we use that x value of 10. If we were to plug that into our volume formula here, we're also going to get a volume of 0. And again, we're trying to maximize the volume, so having a volume of 0 is kind of a bad thing. So really, we're focusing on this 3.68 as that x value. Now, if we were to take that and store key that in our calculator, we're going to get a volume of about 820.5 cubic inches. So that's going to be our maximum volume. If we cut out squares with a side length of 3.68 inches out of the corners of this rectangular sheet of tin, then we're going to be able to maximize our volume at 820.5 cubic inches. Now, in this example, we're going to be designing a 1-liter oil can that's shaped like a right circular cylinder, and we want to figure out what dimensions are going to use the least material. Now, there's two formulas that are really going to come into play here. The volume of the can that we're building is going to be important because it has to hold 1 liter of oil. But then as far as the material that we're actually using, that's like the outside of the can, so we can consider that our surface area. So first, let's talk about the volume of a cylinder. When you're calculating volume of a circular cylinder, it's pi r squared times the height. Now, our volume is 1 liter, but I'm actually going to convert that over into cubic centimeters. So in 1 liter, there are 1,000 cubic centimeters. So I'm going to plug that in for my V value over here. We know that our volume has to be 1,000, and that's going to be pi r squared times the height. Now, as far as the surface area of our can, the formula there is 2 pi r squared. That amount comes from the circular bases on the top and on the bottom. But then we've also got 2 pi r times the height. And that comes from the material going around the outside of the can. Now, when we're talking about the least material, we're going to ignore the thickness of the material that we're using and just focus on coming up with some radius and some height for this cylinder that are going to make the total surface area as small as possible while also still containing this volume of 1,000 cubic centimeters or 1 liter. Now we want to be able to take these two separate formulas in here and sort of combine them into one. We've got too many variables right now. We've got an R value and an H value. So it's going to be helpful if we can get this written in terms of just one variable. And I'm looking at this volume formula over here, thinking that it should be fairly easy for us to solve to get H alone. All we would have to do is take that pi and that R squared and divide it over to the 1000. And then what I can do with that is in my surface area formula, I can plug that in for the H in here. So then my surface area formula is going to say 2 pi R squared plus 2 times pi times R times 1000 over pi R squared. Now there's actually going to be a little bit of simplifying that we can do on the back end here. I see this times pi right here and this divided by pi right there. Those are going to cancel each other out. I see this times R right here, and we've got a divided by R squared. So this times R will cancel out one of those R's on bottom. So then we're going to end up with 2 pi R squared plus, well, if we take 2 times 1000, then we get 2000 over R. So this surface area formula right here is what we're going to work with. And like I said, we're going to try to minimize the surface area while still having this volume of 1000 cubic centimeters. Well, anytime we're doing optimization, we want to take a look at finding the derivative. So I'm going to say the derivative of my surface area formula. Well, with this first piece, I can just use the power rule. The 2 and the pi are just constant multipliers. If I drop the 2 down, that's going to be 4 pi R. Now on the back end, this might be a little bit more difficult since we've got a fraction in there. But what we could do is take this piece, and really we could swing that R up to the top by making it 2000 times R to the negative first. Then if I do power rule with that, drop the negative 1 down, and this is going to turn into negative 2000 times R to the negative second. But I don't like having negative powers, so I would drop that R back down to the bottom of our fraction to make the power positive. So then this will say minus 2000 over R squared. Now to find our critical numbers, I'm going to take this derivative that we just came up with, and I'm going to set it equal to 0. I'm going to add this fraction over to the right-hand side. So I'm going to get 4 pi R equals 2000 over R squared. And then I don't like dealing with fractions, so I'm going to take this R squared that's in the denominator and multiply it over to the left-hand side. So then this will say 4 pi R cubed equals 2000. Then I'm going to divide the 4 over to the right-hand side. So I get pi R cubed equals 500. I'm going to divide the pi over, so I get R cubed equals 500 over pi. And then I want to cube root both sides in order to get R alone. So if we cube root that fraction on the right-hand side, we're going to get about 5.42 if we round that off to 2 decimals. Now I'm going to scroll back up here. As far as the domain of our function, we never really talked about that. We're just trying to come up with some radius value that's bigger than 0. So there's not really a closed interval that we're working with here, so we don't need to necessarily worry about any endpoints. We're just going to worry about this R value that we just came up with. So that radius tells us one piece of information that we need, but we also need to figure out the height of the cylinder that we're going to be working with. So if we were to take that R value that we got and plug that into our height function from earlier and type that into our calculator, that's going to give us a height of about 10.84 centimeters. So we can say that our 1 liter can that uses the least amount of material as far as its surface area goes has to have a radius of 5.42 centimeters and a height of 10.84 centimeters. That's going to be it for this video. Thanks for watching.